All right, good morning. Today we'll look at a few more simplified versions of the equations for the transport model. Then we'll look at a couple of problems. Okay. So, all right, so stop here. So the transport model we looked at the two PN junctions in a BJT represented equally by a diode. This is an NPN transistor. This is the PNP. In the NPN, currents going into the collector, coming out of the emitter. Okay. This direction, collector to emitter. In a PNP, it's the opposite. So it's the emitter to collector. All right. Total current is referred to as IT, and we know IT is the sum of the current in the forward and the reverse. So forward current and reverse current. So IF minus IR because they are moving in the opposite direction. And the equation is listed right here. The only thing that changes with respect to PNP is that the reference direction and the reference polarities are all interchanged. On the output side, we are modeling this as a constant current source. Constant current source. And you will see in later models, we will use this kind of dependent current source model to solve for circuits. So it's a dependent current source. Dependent on voltage or current. On the input side, we could vary the base voltage, the base emitter voltage, and we can control the current on the output side. Or in other words, we can also control IB, the input base current or the base current being sent into the BJT, and then control the collector current on the output side. So on the output side, we can say it behaves like a constant current source. It supplies current, and the dependency is on either the voltage or the current on the input side, on the base. Okay. There are a couple of practice exercises, I believe in the text. It should be section 4.4, I believe. Practice exercises. Okay. So please take a look and go through those exercises. Okay, then I believe you already looked at this slide, which is the different operating modes of a BJT, right? We have the forward active mode, simply referred to as active mode, and then you have saturation and cutoff, and then the reverse active, which we basically reverse bias both junctions, meaning there is no activity going on in the BJT. Then there are biasing modes. Biasing modes, again, goes back to the DC bias that we apply to the device, right? We are setting up the device to operate within some constraint. So we apply DC voltages on the input and the output side, and we are forcing the device to operate in a particular region. We can force it to work in the active region, or we can force it to work in the cutoff and saturation region. That's the biasing mode. So depending on which of the three terminals is common to the input and output side, is how we describe these three biasing modes. Okay, so the biasing mode is which terminal common to both input and output sides. Okay, common emitter is when we have the emitter common to both the input and the output. And again, we'll restrict our discussion only to NPN transistors, but it applies equally to a PNP transistor also. So here, emitter appears on the input side. And again, typically, you should all be familiar with the standard accepted convention. If you look at a circuit diagram, typically the input is always drawn towards the left, right? Input on the left, output on the right. So this would be the input side, and this is the output side. Okay, so that's the common emitter mode. In the common base mode, the base is common to both sides. And this is something you will simulate in the lab next week. Common base and common emitter mode characteristics. So emitter, base, and collector and base. Okay, so that's the CB mode. And then we also have the CC mode. Okay, where the collector is common to both sides. There are advantages and disadvantages of all three, but common emitter by far has the most advantages. So CE mode is the most popular, which is when you'll bias the transistor to work in the active region. That's in lab 8. CE mode, a BJT circuit would provide high impedance or high input impedance. Low output impedance. And typically you can make the circuit work with a single power supply for biasing. Okay. So the next few slides, our discussion would be for the CE mode of a BJT, CE operating mode. So far, so good. Okay. So in the common emitter mode, here are the output characteristics of a BJT. In the common emitter mode, the output is taken at the collector with reference to the emitter, right? VCE. And so you have collector current IC as a function of the collector emitter voltage VCE. Characteristics might look a little similar to the FETs, but there are some key differences. Okay. This right here is defined as the saturation region. Okay. So there is a slope, and the characteristics might appear linear in that region, but that is defined as a saturation region for a BJT. In an FET, this was known as the linear region or the triode region. This is cut off right here when the output is essentially turned off. And then this right here, all of this is the active region. Okay, active region. In an FET, this active region was known as the saturation region. So again, key differences. In a BJT, the mode of operation here in this big area of the graph is the active region. To the left is saturation, and below, close to the x-axis, is the cutoff region. Here, the BJT is set to be off, and here in the saturation region, it is set to be on. Right, cutoff and saturation. And then, of course, we have the reverse active, which looks exactly like the reverse bias characteristic of a standard PN junction. Okay, we would not use the BJT in that reverse characteristic region. In the active regions, so two important voltages that we keep in mind are VBE and VCE. Okay. In the active region, the base emitter junction is forward bias. So VBE should have a value of anyone? 0.7. Why not 0.2? Well, you could have 0.2 or 0.3 if you have a germanium transistor. Slightly trick question. It's silicon. Yeah, so 0.7. But as engineers, you should always keep that in mind. If you're working with an unknown transistor, let's say, and then your assumption is it's an active mode, you measure VBE, it doesn't turn out to be 0.7. Well, it's the transistor material, might not be silicon. Anyway, you had a question? Okay, so the question being asked is, why are we looking at the collector and emitter as the output? Oh, why do we have different sources? I mean, why do we have different sets of curves? Oh, okay. Question being asked is, why do we have a current source on the input side? Okay, that's a good question. Yeah, typically it's easier to actually model the transistor with a controlling input current. You can also model it with a controlling voltage, which is VBE. But with VBE, one of the things is that the change in VBE would be very, very small. IB, we can show 0 microamps, 10 microamps, 15 microamps. Again, it's a small change. But IB comes from the fact that we are applying some sort of biasing voltage at the base. So we can model it both ways. So the answer to your question is yes, we can use current as the controlling factor, or we can use voltage as the controlling factor. In both cases, it will work. Yeah. Typically, we have always used IB, the base current. But the base current is set by the voltage we apply at the base. And we will see that in just a few, well, actually not today, but the next few slides after that. Yeah. Okay, so where was I? VBE. Yeah, VBE, if it's in the active region, should be 0.7. And meaning if it's forward bias. If it's forward bias, it's 0.7. Now, if it's in saturation, what would be VBE? It'll still be 0.7, because if it's forward bias, then it's 0.7, right? If it's forward bias, it's 0.7. But primarily, we start with stating that in the active region, VBE is 0.7. And then saturation, what do you notice about VCE? Saturation region is to the left. Right? Saturation region is to the left. So VCE is typically very, very small, right here. Very close to 0. But we do not take it as 0. Okay, VCE would be approximately 0.2 volts. So if you perform an analysis and it turns out that VCE, the collector to emitter voltage, is 0.2 volts or less, then more likely than not, actually 99%, can always say transistor is in saturation. And the reason it's in saturation is because there is a heavy current that is flowing through the transistor. And because there's a heavy current flowing through, it acts almost like a short circuit. And so VCE would be very, very small. And there's also something known as transistor being on the edge of saturation, EOS, edge of saturation. That's when we would say it's about 0.4 volts or less. And it's not yet fully into saturation, which is basically somewhere right here. And I'm exaggerating the values. And there's an analysis that we can perform for this region also. Approximately equal to 0.4 volts or less. Okay. All right, let's take a closer look at just the active region right there. So we take a look here. And again, you have an entire set of data for each value of IB. As the input current increases, the collector current increases accordingly, right? It's a direct relationship. IC is beta times IB. So each set corresponds to one input value for IB. Okay, if you notice, unlike an FET, this is not flat, has a slight upward tilt or slope. Okay, the slight upward tilt, meaning, yes, as we keep increasing the voltage, the current keeps on increasing right here, but it doesn't flatten out. There's also, in different modes, there's also a region where I think it's in collector base and collector current. I mean, common base and common collector, where the curves actually tend to go up. The reason for that is the junctions break down and a heavy flow of charge carriers can cross over the junctions. But that's when you increase it to like 40, 50, 60 volts. Okay, we are not doing anything like that in the lab or in any of these circuits. Okay, analysis. using the load line would require you to draw load lines both on the input and the output side. So on the input side, we have the base emitter junction. We'll look at those characteristics in just the next slide. But this is the output characteristic, right? So it's IC as a function of VCE. So if you're trying to find the output voltage and the output current, meaning the Q point operation, we can use load line analysis by first applying load line analysis to the input side, then transferring over those data points onto the output side. And later on, we will actually do an example on how to do that. But the process would remain the same. We have done that for diodes, Zener diodes. And so we'd apply KVL, obtain 2 points, draw the load line. And on this load line, we'd find a point somewhere near the center. Okay. And that would be our Q point. If you wish to use the amplifier, if you wish to use the BJT as an amplifier, we want the Q point to be somewhere in the middle of that active region. So that when when an input signal arrives, the voltage and the current does not exceed or go outside of the active region. Okay. So we'll do an example later on. If your Q point is over here, up near the saturation region, and now you're trying to actually have a signal amplified, the peaks of your signal might get clipped or distorted. Again, you would bias your transistor without any AC input signal. Your transistor would be in the active region. But when the AC input signal arrives, you might end up driving your transistor either into cutoff or into saturation. Okay, so biasing is very important. So that's up there. You could end up biasing your transistor right here. The reason I'm going over this is because we'll use this technique to actually design your amplifier for Lab 8. Okay, you will use load line analysis. Well, there are two different techniques. You can use analytical equations, and you can also use graphical load line techniques. And as I said, we'll again look at it later on in this chapter. But you will use that technique to bias your amplifier circuit for Lab 8. All right. Transfer characteristics. Transfer means how the input is transferred or related to the output. In this case, our output is the collector current, IC. And here we are using input base emitter voltage, VBE. Okay. Transfer characteristics, output current as a function of the input voltage. What do you see here? Similar to diode characteristics. Yeah, it's similar to a diode characteristic. So that's the linear scale. If you plot this on the log scale, you can see that on the left is linear. Right, it's log, and that's the result of the same data points plotted on the log scale. The log scale, the movement is linear. And the approximate movement is about a decade change for every 60 millivolt change in the input voltage of VBE. So if VBE increases or decreases by approximately 60 millivolts, then the output collector current would correspondingly either increase or decrease by a factor of 10. Okay. So a very small change in the input base voltage and the input base current would create a correspondingly large change at the output collector current. Okay, that's the device physics. Very small change at the input base side would create a large variation on the output side. The same, going back to that same point in questions that you had earlier. You're injecting holes into the base. How does a small amount of holes create a large collector current? It's just device physics. Yes. VCE, because you want to look at, oh, here, VCE, we looked at that here. IC versus VCE, output characteristics. When we say input characteristic, meaning we're only looking at input current as a function of the input voltage. When we talk about output characteristic, we only look at output current as a function of the output voltage. Transfer characteristic would be how is the input quantity being transferred to the output. And in this case, the input quantity we are looking at is the voltage, VBE, and seeing how it transfers to the output. We could also say a plot of collector current as a function of the base current IB. That would simply be a plot of how the current is being transferred from the input to the output. There are, so I believe the question being asked is, why are we looking at this specific quantity? It's, we can look at all of them. We can look at all of them, but we need like a whole entire academic year if you want to discuss all of them in class itself. So we present the most important portions, and the other portions, of course, is left for outside of class studying. Yes. VCE is a, so question being asked is, does this assume that VCE is a large value? Not necessarily. Not necessarily. If VCE is small, it will be in saturation. May or may not be. We don't know any other information from this circuit. We only know collector current. If collector current is high, you would assume that VCE is low, which would be around here. So you're referring, if I understand you correctly, you're referring this end of the graph versus this end, right? If we look at, let's say, VCE equal to 1 volt and VC equal to, let's say, 15 volts, how much of a difference do we really see in the IC? And this, keep in mind, this slope is also exaggerated. So let's say at 1 volt, it's about, I want to say 35, 36, 37, maybe 38 milliamps, perhaps. What do you all think? At 1 volt VCE, approximately 38 milliamps, right? And then at 15 volt, it would be about 45, maybe 45 and a half or 46, let's say. Difference of like 8 milliamps. So 8 milliamps is not small, but in the context of a change of like 1 volt to 15 volts, current only changes by 8.008 amps. So not a large difference. So we would not be able to predict. Anyway, going back to answer your question, just looking at the current right here, we would not be able to just predict whether VC is higher. Yes. Well, emitter collector current is a factor in the emitter current. They're almost equal. Except for the base current, collector current and emitter current are almost equal. So if we say IC is beta, IC is beta times IB, IE is IC plus IB. So it's beta IB plus IB. So IB times 1 plus beta. Yeah. But again, going back to that earlier point, we only look at the equation collector current as a function of the base current. Right? IC is a function of IB, but then IE is also a function of IB. All right, does that answer all questions for now? Okay. All right, so that was the transfer characteristic. And let's look at the circuit model in the forward active region. This is where we'll spend most of our time. The next two examples are also related to the forward active mode. Okay. So here is VBE on the input side, and here is VCE on the output side. Okay. So let's break it down. Cut in half. You have emitter that is common to both sides. On the left-hand side, on the input side, we have the base emitter junction forward bias. We can model that as a forward bias PN junction with a constant voltage drop of VBE. It's right here. Forward bias PN junction diode. On the output side, it's a dependent current source. So dependent current source. Oh, sorry. Okay. Then we can write the expressions. IC is beta times IB. Standard expression for IC is IS times e raised to VBE over VT. Okay. We can look at it as a current source that is dependent on IB, right? Beta times IB. So here, the dependency is on current. So we can say current dependent. And if you wish to look at the voltage, then it's voltage dependent. As an engineer, you get to choose which model fits your application the best. Right? On the input side, we have the input voltage VBE or the input current IB. The output side, we can label it as a dependent current source that is controlled by the input current IB. Or we can also alternatively model it as a current source that is controlled by the input voltage VBE. So we can simplify this with a constant voltage drop model. And use it as a voltage source of 0.7 volts. Okay. Then we can write simplified equations for all three currents. Okay, IC, IB, and IE can all be written as saturation current IS times E raised to VBE over VT. Keep in mind, IS and VT, for all intents and purposes, would be constant at a particular temperature, right? The only variable would be VBE. VBE changes, then IC changes. And IE can be written as IS over alpha F IS over alpha F into E raised to VBE over VT. Then we have IB. Since we already have IS, all we need to do is divide by beta. These are the simplified equations. Again, as engineers, let's say we're analyzing a circuit, you want to get a quick answer, right? The most efficient method possible. Then you want to minimize as many variables as possible. You simply take the simplest possible equation, plug in your values, get an approximate answer. Once you obtain an approximate answer, if that suffices for your application, if it suffices for your purpose, then great. If you want a more accurate or better answer, then you apply a different model to that same circuit and go on, proceed from there. Okay. So there are about 13 minutes left. I want to get through 2 examples. Okay. So let's look at example 1. Straightforward example, there are no resistors in the circuit. We're simply applying biasing voltages and currents. On the input side, we have a base current or current source that is biasing the base. On the output side, we have a voltage that is biasing the collector terminal. Okay. So VCC is applied to the base. VCC is applied to the collector, and a current source of 100 microamps is applied to the base. Okay, no other resistors. We look at resistors in example 2. The given information is that IS saturation current is 10 raised to minus 16 amps. Alpha F is 0.95. Whether it's given or not, you can assume these values. Okay, you can assume these values. Let's say I would just give you the circuit and I'll say find the collector current, collector voltage, base voltage, and collector voltage. Whatever is not given explicitly stated in the problem, you can feel free to assume. All right, so the question being asked is determine IC, IE, VBC, and VBE. Assume VT, thermal voltage, is 25 millivolts. All right. So these are the givens. Let's say our assumption is that the transistor is operating in the active region. Okay. From the current source, it's going into the base, and the collector emitter voltage applied VCC, we can assume active region of operation. If we assume active region of operation, we can conclude that VBE is 0.7 volts. Right? VBE is 0.7 volts. So right off the bat, the emitter is common to the input and output side. So if emitter is at 0 volts, VCC, meaning VC, collector voltage, is at 5 volts. Since VC is at 5 volts, I can derive VBC directly as VB minus VC, meaning in this case, VBC is minus 4.3 volts. That is solely based on our assumption, right? We are assuming VB is exactly 0.7. We don't know if it's 0.69. We don't know if it's 0.71. But we begin our analysis with an assumption of 0.7 volts. So we find VBC as minus 4.3. Then we can find IC. Okay. That's the next step. So the IB. In this case, it's convenient that it's a current source, so we don't have to find IB. And this would be alpha over 1 minus alpha. Okay, plug the values and solve for IC. Alpha is 0.95. 1 minus 0.95. And IB would be 100 microamps. And therefore, IC is 1.9 milliamps. Okay, IC is 1.9 milliamps. Once you have IC, find IE. Two milliamps. Yeah, sure, a different way, but obviously IE is simply the sum of IB and IC. So 1.9 milliamps plus 0.01 milliamps. It gives you 22 milliamps. All right. And now that we have that, let's use that to find VBE. Okay. From our previous equations, we can find VBE as C or IS. So 0.025 log of 1.9 milliamps and our saturation current of 10 raised to minus 16. And for our VBE comes out to 0.764 volts. Our assumption initially was 0.7. Our value turns out to be 0.764. Now we can go back and use this VBE to find again and keep iterating if we needed to. In this case, we don't need to, right? We already found the exact value for VBE. The current is also fixed because it's a 100 microamp current source. There's no other resistor in parallel with the current source to divert that base current, okay, or to reduce the base current. And one final step would be to find the final value of VBC. Since VBE is changed, VBC would now be 0.764 minus 5. So the actual VBC value would be minus 4.24 volts. Okay. We found it as 4.3 volts earlier. Okay. There's 4.24. Make sense? All right. Less than 5 minutes left. Okay. Let's go on to the next one then. With a bit of a rush. If you need to leave at 12, feel free to do so. I will continue recording until the problem is finished solving. All right, forward active example number 2. Base, there is no power supply. It's connected directly to ground. However, there are 2 other power supplies, positive and negative, dual biasing to allow for bipolar voltages and currents to flow through. So we have VCC at plus 9 volts and we have VEE as minus 9 volts. Base is at 0. That means it's 9 volts above the emitter. Okay. All right. So beta F is given to us as 50. Beta R is also given, which is 1. We're asked to find the Q point. Okay. That's the only information that is given. All right. Q point means we need to find the collector current and the collector voltage, or VCE. Okay, collector voltage with reference to the emitter. So let's assume active region. And therefore we can write VBE is 0.7 volts. Now, in this case, the standard technique still applies. We have the input on the left, output on the right. I want to generate equations. I have resistors in there, so I'm simply going to apply KVL on both input and output loops. All right. So apply KVL to the input loop, and I obtain VBE plus IE RE. I'm gonna name this resistor RE. Okay, that's the emitter resistor RE. Makes things easier to remember. Okay, so that's the voltage drop across the RE resistor, and then I have minus VEE. Be careful when applying KVL to negative voltages, okay? If you take a minus sign in the equation, you don't need to put a minus sign again. All right, plug in the values. We get 0.7 plus 80 to 100 RE minus 9 volts gives you 0. Therefore, you find IE. So from the input side, I can find IE. Once you have IE, you can find IC and IB, right? So alpha is not given to us, but beta is. We can approach it 2 different ways. We can first use the beta values to find IB and then find IC, or we can compute alpha from there and find IC. Either ways, doesn't really matter. So let's write it this way. Since IE can be written as beta plus 1 IB, I can find IB as IE over beta plus 1. In this case, it'd be 1.1 milliamps divided by 50 plus 1. gives me 19.3 microamps. 12 o'clock. 19.8 microamps. Okay. And IC, therefore, is beta times IB, and we get 0.99 milliamps. Okay, 0.99 milliamps. All right, then we apply KVL to the output side. I'm going to go from here to here. And you apply KVL on the output side, you get VCE would be equal to VCC minus the voltage drop across the collector resistor, so ICRC, plus oh, actually, let's see, in my method, I did not. So let me do this. Let me explain. When you're applying and you wish to find, you can apply KVL here for output loop. You could also apply KVL in this direction. Does that make sense? All we want is a value for VCE. VCE appears in both loops. If I look at the circuit, VCE appears in both loops, right? Emitter is right here. So I can apply on the other direction, or I can do it with VBE. Okay, so the equation I have VBE, I would say outside of class, practice with the same KVL expression. We have values for IE. You can find the voltage drop across RE as IERE, and you should obtain the exact same value. In this case, I'm applying to I want to say the RC plus input. Okay, that's why I have VBE in there. All right, so VCE would be equal to 9 minus IC is 0.99 microamps, sorry, milliamps times 4300 plus 0.7. And therefore, VCE would be equal to 0.554, 5.44 volts. And that's my Q point. Q point is 0.99 milliamps and 5.4 volts. Okay, we'll end class here today, and I will see you all on Monday. There will be a Monday quiz. I will post the announcement sometime later today after I decide the topics and look at the homework deadlines. No. All right. Yes. Or what? Output is 0.95. I don't think I understand where. Well, no, here, okay, so the question being asked is, can we assume any value for alpha? Well, here the beta value is given to us, so we cannot assume. We can calculate alpha from that beta.